sketching curves with calculus. So here we're just going to start off with a function and we're going to use calculus to sketch it out. So the function we're going to start with is y equals x cubed plus 6x squared plus 9x plus 3. So the first thing we want to do when we're sketching is to find the y-intercept, because that's pretty easy. So we can just make x equal to 0, and if we do that, we'll just get y equals 3, which will be our y-intercept. That's always a good first step. Now, we're using calculus to sketch this curve, so let's find the first and second derivatives. So dy dx is going to be 3x squared plus 12x plus 9. The second derivative is going to be 6x plus 12. We're going to use these to help us find out some information about the curve. Remember, the first derivative tells us about stationary points, and the second derivative tells us about concavity and inflection points, and we can use that second derivative as well to help determine our nature of our stationary points. And that's exactly what we're going to do. So first, we're going to go for stationary points. We know that the first derivative is equal to 0. So we're going to do that. We're going to 3x squared plus 12x plus 9 has to equal 0. We can divide everything by 3 here. So we'll get x squared plus 4x plus 3 equals 0. Let's factorize our quadratic. So two numbers that multiply to 3 and add up to 4 will be positive 3 and positive 1. And solving here is going to give us x equals minus 3 and minus 1. So they're the x coordinates of our stationary point. We need the y coordinates. So when x is minus 3, we're just going to sub in the original function. So we'll have y equals minus 3 cubed plus 6 times minus 3 squared plus 9 times minus 3 plus 3. Evaluating that gives us 3, and do the same thing for x is minus 1 is going to give us a y value of minus 1 as well. So now we found our stationary points, but we need the nature of them, and we can use either the first or second derivative to determine the nature. So you could do the table and checking either side of the stationary points with the first derivative and checking the gradient, or you could use the second derivative to determine the concavity at these points to tell you if it's a maximum or minimum. And we're gonna use the second derivative. So all we need to do is sub in those points in the second derivative. So let's sub minus 3 into the second derivative. So should say here we're determining the nature of our stationary points. So we're subbing in. So we're using the second derivative method. So we have 6 times minus 3 plus 12, which gives us minus 18 plus 12 to give us minus 6. So we get a negative value for the second derivative, which implies the curve is concave down there. And if the curve is concave down, that means we've got a maximum turning point. Do the same thing with the other stationary point, which is minus 1. Put it into the second derivative. That's going to be minus 6 plus 12 to give us 6. Because that's positive, we get a concave up curve, which implies a minimum turning point. So we can say, therefore, the stationary points are minus 3 and 3. So we're using that y value, and we know that's the maximum. And we know we've got minus 1, which is a minimum. So we already know some information about the curve now. So let's graph some things we know already. So we know we know we have a y-intercept of 3. We have a maximum turning point at minus 3, 3. We have a maximum turning point here. And we have a minimum turning point at minus 1, minus 1. So we have a minimum turning point here. So we know we've got a minimum turning point and a maximum turning point, and we have enough information to do our graph now. But we're just going to go ahead and find the point of inflection as well. So for our point of inflection, that's where the second derivative equals 0. So we're going to do that. We're going to take our second derivative of 6x plus 12 and make it equal to 0, and we're going to solve for x. So we'll minus 12 from both sides, then divide both sides by 6. So we get x equals minus 2. And we need to find the y-coordinate. So we're going to sub, using x equals minus 2, we're going to sub it into our original function of y. And if we did that, we're going to get 1. So just subbing it into our original function, we'd get 1. But for any point of inflection, we need to test. We need to always test to see if the concavity changes across, and we use our table to do that. So now we're going to test for the inflection. So we'll make our table. And we want to check on either side of our inflection point what's actually happening in our second derivative. So this is minus 2, so we're checking on either side, so we'll check for minus 3 and minus 1. We know if we sub minus 2 into our second derivative, we get 0, because that's how we got it in the first place. If you sub minus 3 into the second derivative over here, so we get 6 times minus 3, which is minus 18 plus 12, gives us minus 6. Then we can sub minus 1 in to our second derivative. 6 times minus 1 is minus 6. Minus 6 plus 12 is positive 6. So we get a negative value for our second derivative on the left, which implies the curve is concave down on the left, and a positive value on the right means the curve is concave up. So then we can definitely say that the concavity is changing, so therefore concavity changes, and therefore our inflection point of minus 2, or possible inflection point, actually is an inflection point. So therefore minus 2, 1 is an inflection point. And let's go ahead and graph all of that now. So we know we've got our maximum turning point up there and our minimum up there. So it must be doing something like this, coming and back around, and we have the y-intercept of 3, so it has to go through there. And our inflection point was at minus 2, 1, which somewhere about there. So we can even go ahead and label these points in: minus 3, 3, minus 1, and our inflection point at minus 2, 1, which makes sense because that's looking like it's concave down and that's concave up, and we're expecting a change in concavity in the middle there.